So since we have this effect of the difference between the maximum and the minimum stress, you can also make this difference on the influence on the average stress. So how does that turn into the curves they use in lifting appliances? You have basically two curves. If I have a maximum stress and a minimum stress, I divide the quotient of the maximum divided by the minimum. By the way, the minimum divided by the maximum. If the maximum stress, if the minimum stress in compression, so the compression stress is bigger than the tension stress, if that's the maximum, then these two swap. Yeah, it is not the minimum and the maximum, it is basically the absolute maximum where you divide by. Yeah, and you take, if the signs are different, then you get a -1. And then you get here these curves which depend on whether it's tension or compression. And then for situations where the sign of the stress is varying between between the maximum value and the minimum, or between, if the sign stays the same, I get some kind of an allowable stress. Yeah, so the difference between tension and compression, you can see that. So this is the compression limit and that is the tension limit. Here you can see this is the average stress. You can see that the value here, it decreases, while here the difference stays the same. And these are parallel, while these two numbers in the end they run into this point. So there is the effect of the average stress is taken into account by slightly decreasing stress variation depending on the average stress. Okay, if we want to, so this is the way how to calculate this stuff. But if I'm in the design phase, then I say, okay, how do I use this? And I think that is the beauty of these lifting appliances standards, because there you can do the opposite. I can easily qualify what type of connection I have, so whether I have a K0 to K4, and the crane group, I know the material, and then I get some kind of a curve based on the limit stress ratio. So if I know on a certain point my maximum stress and my minimum stress, I take the quotient between the two, and be aware that if the minimum stress is bigger than the absolute minimum stress is bigger than the absolute maximum stress, the sign swaps. But then I get, based on this limit stress, so the minimum and the maximum, the quotient between the two determines what kappa value I have. So that is this stress ratio, and based on that, so suppose I have either a load or nothing, then my limit stress ratio is 0, because then the minimum is 0 and the maximum is the maximum stress. So then I can use this curve directly and say, okay, what is my allowable stress in this situation? Yeah, so for Eurocode and 13001 and other detailed, or the DMV, they have detailed procedures with load cycles, and that is a nice idea. But the beauty of the method of lifting appliances is, if I know my classification, so I have an idea on the number of load cycles, I know what what the classification is for fatigue on a certain spot, I can directly come up with a curve and then check, okay, what is my allowable stress? And then you can see, so if I have or no stress or a maximum stress, I can also see the devastating influence for using lower, so for not paying attention to fatigue. If I make connections like this, so no avoidance of stress concentration factor, then I end up with a K4. Then my allowable stress is only 45 megapascals. Yeah, and if I do have welds, but I make it nice, yeah, so I can come up maybe to K0. Maybe that is too hard, but K2 is easy reachable. I have 100 megapascal allowable stress. Yeah, so with curves like this, you can, in the design phase, this is a great standard. And because you can in the same way as you calculate your static limit, you only have a limit which varies on the weld detail. Yeah, and you can in this method you can clearly see that it pays off to deliver quality work. Yeah, because the higher, the better the notch group. So the more attention you pay to avoiding stress concentration factors, the higher the maximum stress you can allow. Okay, so again, so how does that result? You have classifications on the welding. I skipped the welding a bit, so this is no weld. This is a perfect weld with grinding, as you can see. This is a standard weld, just welded, no grinding. Then I have a K1. K2 is if I have the same thing welded, but I do have crossing and a bigger scale, so shrinking can become a problem. Then I have K2. K3 is with a backing strip. And so you can see that already if I have a backing strip, then I'm maximum in this category. And it's hard to upgrade. Yeah, and then if I have, for example, some kind of a crossing situation where two plates need to be welded, here, double baffle weld of ordinary quality, that is I think that is a category class 3, and if I use fillet welds, is K4. So it gives you advice on the welding types I can use. That is the first thing. And I can also see that if I make thick plates to thin plates within a certain category, I end up in K4. Yeah, and that basically, if I have a situation where I have lifting appliance crane group 6, so I have 2 million loads to lift and lower, my allowable stress is only 45 megapascal. That is compared to yielding, which is 160. That is a huge reduction. Yeah, so the message here is avoid these lower, these high notch classes, or the lower fat classes. Yeah, that's the same thing. And so avoid big stress from thick to thin plates, and avoid, if you have these crossing things, avoid fillet welds if you have locations where stress need to go from one side to the other through a detail like this. And then the same, if I have connections, I have the same method. Stress concentrations like this is a K4 and this is a K2. K3. So for K3, pay attention to that, to the final design of it, and connections like this you should avoid in high stressed areas if you have a lot of load cycles. Yeah, and again, here you can see the allowable stress if you have zero stress or a maximum value. And if you have, of course, this situation where you have tension and compression at the same level, this value dropped to, let's go back to the curve. This is here 27, this is 45, 63, and yeah, so that is especially this one. 27 megapascals as allowable stress. That is really, really, really low. Okay, of course, in other standards, this message is also apparent. In the 13001, we have classes from 355. I can barely read it, all the way to 25 megapascals. Yeah, and that is, you have these classes, you have a classification, welding is included here. Here, let's zoom in here. Oh. Yeah, so you have classifications based on the geometry, and you have special conditions, like a single fillet weld is one class down. Weld quality level D, that is basically, yeah, weld quality level Ds are very often not allowed, because that is just adding a weld without any control, and that is also one class down. So if you are already in, let's say, one of these lower ones, I have 56 megapascal allowable stress for 2 million load cycles, and I need to go 2 classes down more, then I end up 56, 2 classes down, then my stress variation is 40. So 40, that means that my allowable stress, if I have a completely varying stress, is only 20. Yeah. So the impact of fatigue is huge on your design if you have a large number of stress variations. Yeah, and you should also read this standards not as a cookbook. Okay, this is my allowable stress, and let's see what we get. You can also, in the design phase, take into account, okay, if I want to be able to design up to a certain stress level, I need to have a quality at least this. And so you can, if you read it that way, then this becomes an indication book on how to make details. Yeah, if we summarize this and we do a classification according to lifting appliances standards, then we end up with very simple classification. All welds by default are K3 because we don't treat them or do anything. For shear location, it's always K0 because shear, the stress there is no stress concentration because of shear. If I have this one here and I have a weld, if I have here my shear load over my weld, then the main stress is in the middle. Yeah, because of the absence of shear does not become bigger at the edges, so you don't have stress. You have the opposite of a stress concentration. It's always smoothly divided. So that's the reason why for shear, you at a weld, you always have K0. Then for a stress perpendicular standard, it's K1, and perpendicular, it is K3. And then you have a rule, because you have these, you calculate the fatigue damage in the different directions. This is the combination limit. So the stress in the end, the fatigue damage in one direction needs to be below 1, but the summation of the 3 direction needs to be below 1.1. One odd thing of these lifting appliances standard is that if I have a situation where I have let's say a stress in this direction and a compression stress in that direction, I make things worse. So then this minus figure, then this sign is different from that one, and this one becomes a plus. And so then I get the damage of one times the damage plus the other. Yeah, so although this is a logical consequence, this can have odd effects if I have stress variations which are very close with a kappa value close to -1. What does that mean? That means that my stress, my maximum stress and my minimum stress are close by. Yeah, if this one is, let's say, 20 and this one is -20, 21, then this is compression. While if this one increases to 22, then it is tension again in this rule. Yeah, so then the sign here might easily swap. Yeah, so pay attention to that if you happen to have that situation. Yeah, and then again, we have for plate models, or there is no stress concentration, I have these classifications, and if I use a beam model, then I also need to take into account in the classification also how do I connect. Yeah, so again, this is what you want to avoid. Yeah, and I use these color codes that K3 is pay attention, K2 is okay, but K4 is for lifting appliance and no-go if you have a serious number of load cycles. This one we already had. That's a repetition of this. This one we also explained, but that is a re-summary. How do I do that in my SDC Verifier? Calculation schedule. In SDC Verifier, basically you follow the same simple classification method. Okay, what group do I have? What is my weld category? And this weld category can vary per location, and that's basically everything. Yeah, so and the beauty is that all this number crunching is different, so that depends on the maximum stress and my minimum stress. So in every element, if I have a plate element, I have the top and bottom value, and then every corner I have a different result. So I have for one element already 8 maximum stresses and 8 minimum stresses, and this goes through this number crunching, and that is done automatically for your full model, and then you get pictures like this. Yeah, so that is a huge time saver. Of course, this standard was intended to do by hand to get to an allowable stress, but if you want to do control calculation, SDC Verifier makes your life a lot easier. Yeah, again, if we have a plate model, we have all these welds, we have the different classifications, and then you get results like this. Yeah, and for volumes, there is not really, that is a bit of a problem. Besides that, nobody wants to calculate with volumes because your models get really big. It is also classification-wise an issue, because all the examples you see in these classification in the older lifting appliances results, they don't make a difference between volumes and plates, and in volumes also the stress concentration of the design itself is taken into account. So I just transfer that into a better quality, a K2 for all my welds, which stresses perpendicular to the line, and K1, because the stress concentration, like in a detail here, is then already included in your model.